behave, you're welcome to come to dinner at 6:45 and let me know right after the talk. As the usual case.
Thank you, Greg. So I'm talking about today a technique that helps you in a combinatorial situation that I have found myself in a lot lately, which is you're investigating some kind of combinatorial sequence, and somehow you manage to obtain a large number of initial terms of the sequence. Maybe it's a dynamic programming trick, or maybe something else, but you've got a large number of initial terms, and you don't know what to do with them. And what can you do with those to try to find out something about what you're studying? As the running example for the techniques, I want to talk about a particular sequence that I found recently that is pretty interesting, I think. So first I'll define what the object is. A chord diagram, aka a matching, or sometimes called an interconnection network of size n, is a set of n arcs connecting two endpoints in a line. I'll give you an example. An example of a chord diagram of size 4, well, it means we have 4 arcs, so we need 8 points. And I connect them in pairs. So the example that I'll give you is the first one is connected to the 7th one. The second one is connected to the 5th one. 3 goes to 8, and 4 goes to 6. So this is a chord diagram. And the number of these is the double factorial numbers. That's pretty easy to see. It's a very well-known sequence. This one, does this move? Yes. What I want to look at is...
So you have to link the first half to the second half, or?
No, that's just how this one turned out. Yeah, there can be any pair. So for example, the 3 chord diagrams on 2 arcs are this one, that one, and that one. And then I want to look at a subset of these. A chord diagram is 2 colorable. If there exists a red-blue coloring of the arcs, such that no 2 arcs of the same color cross. So for example, the example I gave you above, this is 2 colorable, because I could color these first 2 arcs red, and these second 2 arcs blue, and then no 2 red arcs cross and no 2 blue arcs cross. An example of something that's not 2 colorable is this. No matter what you try to do, you can't color these such that no 2 reds cross or no 2 blues cross. And this is the sequence that I'm going to use as my example. So we'll let A sub n equal the number of 2 colorable chord diagrams. And I'll give you the first few terms here. A sub 0 is 1, and then there's 1 on 1 arc. 3, the 3 I drew up here on 2 arcs. And then it goes 14, 84, 592, and so on. This sequence has come up in a couple places recently. In 2014, Michael Albert and Mireille Bousquet-Walou counted the number of permutations that are sortable by 2 stacks in parallel. And that's closely related to this, because you can treat the red arcs kind of like a stack, where the opening of an arc is pushing into the stack and the closing is pop. You can treat the blues the same way, and then by making some certain adjustments to that, you're restricting to the case of permutation. So this showed up there. Also in the recent PhD thesis of Vince Vatter's other student, Aziza Jefferson, and she was looking at genome rearrangements, and it came up there. Now, as for what I've done with this sequence,
How many terms do you know?
I'll tell you in 1 second. As for what I've done with the sequence with Peter Doyle at Dartmouth, we've come up with a functional equation for this that's some kind of composition of things that we already know, and implemented it in a dynamic programming way to get 1,500 terms of the sequence. And that's basically just where we got bored and we stopped. We could probably get 10,000 if we thought that it was going to help us in some way. But despite this, we don't know much about the sequence. We don't know rigorously what the asymptotic behavior is, what's the exponential growth rate, anything like that. So the techniques I'm going to talk about today will help us figure out that kind of information numerically and experimentally from a sequence of initial terms. So we're looking at the question, what do you do with a bunch of terms? Okay, well, hopefully as combinatorialists, we all have the same step 1 when you have a bunch of terms, and that's check the OEIS. I didn't just add that in, that's actually still here. Check the OEIS. So you do that with this sequence, and unfortunately you don't get any results about Michael Albert's paper. You get results about Aziza's PhD thesis, which is great, except they only have 8 terms, and it was one of many things they looked at, so they didn't actually find out anything about this other than 8 terms. So for this particular sequence, we have no luck.
You might try super sequence.
Yeah, so step 2 is in that vein, and that's search for an exact form. And I know Superseeker does some of that. By searching for an exact form, what I mean is use one of the many tools that are out there to try to automatically conjecture the exact value of the generating function. One popular tool is called gfun. It's part of Maple. Drone has a number of programs that do things like this as well. Mathematica has a suite of programs, and I have my own program that does kind of the same thing as gfun, but with an extended type of form that it looks for. I'll mention that later if I have time. So anyway, you search for an exact form. What gfun does is it looks for a d-finite generating function that matches the initial terms. Okay, so let me define what I mean by d-finite. The generating function f of z is d-finite if it satisfies a non-trivial linear differential equation. So for example, something like p sub k of z, this is a polynomial, times the kth derivative of f, all the way down to p1 of z times f prime, plus p0 times f, and then we'll allow the inhomogeneous term, even though it doesn't really make a difference for our definition. And I didn't say it, but the pi's must be rational polynomials. Okay, so if you satisfy a linear differential equation, you're d-finite. There's a lot of great things about d-finite functions. They have a lot of nice closure properties. The product of d-finite functions is d-finite. Unfortunately, the reciprocal is not, but it does have a lot of nice properties. One other nice property is that it encompasses 2 even simpler forms. This includes the algebraic and the rational functions as well. So gfun looks for, and all these other programs as well, they look for a d-finite generating function that matches the known initial terms that you give it. And there are some smarter ways to do this. Basically, you're setting up some kind of linear system of equations and solving it. I don't have too much time to talk about that. But since this is a talk about asymptotic properties, you can probably guess the result when we try to use gfun to look for an exact generating function. And that is that we also have no luck with our sequence. If it had returned an answer, that would be great, because while it's still a conjecture and it's still experimental, now you know what you're trying to solve, at least. You have something to aim for.
You won't be that great. You won't be as interesting.
Yeah, it wouldn't be as interesting, but it would be at least easier to figure out what's going on. So this fails, and we move on to step 3. Step 3 is to give up on exact answers. And look for asymptotic answers. Depending on who you ask, maybe you should look for asymptotic answers first anyway. Some people think these are more interesting. They give you the behavior as you go to infinity, and for some people that's all that matters. But once we can't do anything exactly, once we can't find a conjecture, we look for asymptotic answers. Move over here now. When you're looking experimentally for anything, really you have to make kind of a conjecture first about what form you're looking for. Jerome would call that picking an ansatz. Once you pick your ansatz, then you can check if it fits. For asymptotics, there's a particularly simple one. A lot of sequences grow like C sub n is asymptotic to a constant times an exponential component mu to the n times a polynomial coefficient n to the alpha. And let me just define this notation in case anybody hasn't seen it. When I say the sequence grows asymptotically like this, I mean that the limit as n goes to infinity of the first side over the second side equals 1. Okay, so a lot of combinatorial sequences have this kind of growth, including the Catalan numbers, which are 4 to the n, n to the negative 3 halves. So one thing you might do is start by assuming your sequence grows like this, and look at the numbers and see if it actually fits. If this is true for a sequence, so if it has growth like this, then one interesting thing to do is to look at the ratios of consecutive terms. So if our sequence grows like this, then the ratios look like c times mu to the n times n to the alpha over c times mu to the n minus 1 and minus 1 to the alpha. You do some canceling here, and you expand this, and you get that this is mu times 1 plus alpha over n plus stuff on the order of 1 over n squared. So if your sequence behaves like this, you expect the ratios to behave like this. Now if I had left out this alpha term and just said the ratios behave like mu, that's also a perfectly good answer. This alpha over n is a subdominant kind of term, but if I know it, I can put it in there and have a little extra information. And this is really the dawn of a technique that was called the ratio method. I think the ratio method really started appearing in papers maybe in the 50s, though it was around before that, and I think a lot of people knew about it and maybe didn't talk about it in papers, and they used it because it's a pretty obvious thing to do once you know this fact about asymptotics. What you do is you let r sub n be these ratios. Thank you. Okay. Now, if you want to figure out if you want to estimate the asymptotic growth rate, meaning you want to estimate mu, one thing you could do is calculate the ratios and look at them on a graph. So one way to do this, which is really the bad way, is to plot the points n r sub n on a graph and look at where the horizontal asymptote is, what they approach as n goes to infinity. Now, this is kind of tough to do because the human eye is not good at looking for horizontal asymptotes, right? That's just something for us, it's hard for us to see when looking at a graph. So the better way to do it is to, instead of plotting the ratios against n, plot them against 1 over n. Now what you're doing is, instead of going to infinity on your x-axis equivalently, you're going to 0. So we're not looking for the horizontal asymptote anymore, we're looking for the y-intercept. This has nothing to do with these actually being ratios, it's just a factor of numbers. If you're looking for a horizontal asymptote, and you turned that x-coordinate from n to 1 over n, now you're looking for a y-intercept.
It's also useful if you're looking for that 1 over n.
Yeah, exactly. So this first step, this is going to help us estimate mu. And let me show you what the plot of ratios looks like for the first 100 terms of our sequence. So we're going to pretend that we only know 100 terms. When we give these points to Maple and tell it to plot it, it gives us this scaling of the axes. It's not very useful. But this is our first point here, 1, 1. And then this is n equals 2, n equals 3, 4, and so on. When I zoom in over there, we're looking for where it hits the axis. When we zoom in, this is what we see. You've got a nice kind of linear shape, which you expect if you have this nice asymptotic form. If not, you'll have some curvature. But we're looking for where this hits the y-axis. And really, at this point, you just kind of hold a piece of paper up to your computer screen and kind of eyeball it and make a guess. So this would tell us, if we're estimating the growth rate, we might think somewhere between 13.3 and 13.5, maybe. That would be kind of a reasonable estimate using the ratio method. Now this is definitely an advantage over just computing the ratios and looking at a list of numbers. Because if we just look at the ratios themselves, for the first 100 terms, we start with 1, 3, 4.67, and then our last two ones are 12.9576 and 12.9614. So this is A100 over A99, and this is A99 over A98. Just looking at the list of numbers, it's kind of hard to say where does that convert, right? Maybe you think, well, it's slowing down, so probably between 13 and 15 might be a guess. But using the ratio method, it's a lot more convincing, and we have a smaller interval. Okay. So there are some other tricks with the ratio method that I'm not going to go into too much, or at all, I guess. One is to, instead of plotting this plot, instead look at every single consecutive pair of points, and for that pair, extrapolate where it would hit the y-axis if they made a line. And then plot those extrapolations against 1 over n. And that improves this too. So if you do that here, you get something like, I didn't write it down, but I think it's something like 13.34 to 13.36 maybe. That's another little trick. You can also use it to estimate the alpha term. But here's where the ratio method really starts to break down. And it's that if you want to estimate alpha, you have to have a good estimate of mu. And if your estimate of mu is off because you've got a sequence that behaves poorly, something like this, maybe with a lot of curvature so you can't really tell where it intersects, then you don't get a good alpha estimate. So it's a good first pass. It gives us a little bit of information, but it's not always reliable when the sequence behaves in any kind of worse way. And now we come to the main topic of the talk, which is a different method to do this. It's called the method of differential approximates. This was invented in the 70s by Tony Gutman, who who's currently at the University of Melbourne, and Joyce, who I think, at least at the time, was at King's College London. And they're not really mathematicians, even though Tony Gutman is in a math department. He's really a physicist. He's a statistical mechanist. But what statistical mechanists don't want to tell you is that they're combinatorialists. They do all of the exact same things we do. They just have different motivations for their problems. So one thing they like to do is look at self-avoiding walks in the plane. You start at the origin, you walk around the plane, but you can't intersect yourself. And that's a combinatorial problem. They just have motivations that come from physics. We have motivations that come from somewhere else. They invented this method for the same reason that I came across it, which is they had lots of terms of combinatorial sequences, maybe 500, maybe 5,000, but they couldn't prove anything about the generating functions. And some of these sequences that motivated them then, they still can't prove anything about them. But using this method, they know a little bit more about them.
No, for self-avoiding walks, they don't have that many.
Not for self-avoiding walks, no. I think it's like 100 and 140, maybe, something like that.
No, but now it's only, but it's way back in the 70s, only at 30.
Yeah, so this is one example. They have other problems like self-avoiding walks on different lattices or other kinds of problems like that.
But back in the 70s, right?
Yeah, maybe they didn't have 5,000 terms then.
Yeah.
Some of them now. So one that they're working on now, for example, is the square lattice Ising model, the susceptibility of the Ising model, and they have 5,000 terms for that. And I ran it through my program to guess exact forms, and it guessed nothing, and so we resort to asymptotic stuff. The differential and differential approximates really just means d-finite. So before I tell you how the method works, I have to tell you a little bit more about d-finite asymptotics. Let B sub n be a sequence with a d-finite generating function then B sub n is asymptotically a linear combination, a finite linear combination of terms that look like the following. So we're basically looking at, in the example that I had on the board under this, you could have mu to the n, n to the alpha. That's a particularly simple form. What can d-finite functions do? Well, for starters, they can have an n factorial to the s, and I'll tell you the restrictions on s and the other variables in a second. They can have the same mu to the n that we saw before, the exponential part. They can have this weird term that's e to the q of n to the gamma. This is a polynomial in n to the gamma. They can have an n to the alpha and a log n to the beta. So it's a finite sum of terms like this. The restrictions are that s and gamma must be rational. Mu and alpha must be algebraic. Beta must be a natural number. And q must be a rational polynomial. So significantly more complicated than the form that we had before, where we just had the mu to the n, n to the alpha. This was proved in the 30s by Birkhoff and his student Trudzinski. And for basically since then, there have been some debates about whether there are gaps in their proof. And it's something like 100 or 200 pages long, and it's very, very technical. But finally, a couple years ago, Igor Pak claims to have found the gaps and plugged them by combining other people's work. So we can now take this as fact because I trust Igor Pak, and then we don't have to actually read these papers ourselves. Okay, so this is
the most general scenario. I think for the special cases that come up in applications, it probably these gaps don't show up.
Yeah, so with certain cases maybe you could work around the gaps, but then you'd have to understand what the gaps are. And that sounds like a lot of work. So we don't want to have to do that. Now we don't need to, which is nice. There's another fact, a simplification here, which is that if your sequence b sub n is exponentially bounded, so it's bounded above by some mu to the n and you don't grow factorially, then it simplifies. We lose the n factorial term and we lose the e to the q term. And we're just left with a finite linear combination of mu to the n to the alpha, log n to the beta. This is actually the growth that most people know about for d-finite functions because it corresponds basically to when you have a regular singularity. Let me give just a quick synopsis of analytic combinatorics to tell you why this is important if you don't know. In combinatorics, we usually start by thinking of our generating functions as algebraic objects, formal power series. But it turns out that if you think of them as complex valued functions, which is weird at first because now you're plugging numbers into them, then the complex analysis of the function tells you a lot of important information about the asymptotic growth. The first example of this is always, I guess they call it the first principle of analytic combinatorics, and that's that the location of the singularities tells you how to find the exponential growth rate of the sequence. I'm fudging this a little bit. Really, it's the exponential growth rate is 1 over the location of the closest singularity to the origin. But you could also have actually a sum of things like this, so this is really like an upper bound on the exponential growth rate. But the point that I want to make is that knowing things about the singularities of our functions tell you everything you want to know about the asymptotic growth of a sequence. Okay, so that's the review that we needed on d-finite asymptotics. And now I'm going to tell you how the method of differential approximates works. So I'll write DA method for sure. Here's the general outline. I'll go over the steps in a little more detail afterwards. The first step is to take your known initial terms and you force them to fit into d-finite form. You force them to fit to a d-finite generating function. Now your sequence usually isn't going to be d-finite, because if it was, you would have stopped at step 2. So if you're here on step 3, it means it's not. I'll talk in a minute about what I mean by forcing it. And really in this case, we're not fitting it to just one d-finite form, but actually many d-finite forms. Many different but similar d-finite forms. And this kind of explains why we want to deal with d-finite generating functions. What we want is something complicated enough to give us interesting asymptotics, or it can't model a lot of things, but easy enough that we actually know how to extract the asymptotics. For example, if we were looking at rational functions, yeah, we can get the asymptotics of rational functions easily, but they don't do much interesting stuff. On the other side, we could use the next level up from d-finite, which is differentially algebraic. That can do a lot of interesting things, but so much so that we have no idea what they can do. So that would be too far on the other end of the spectrum, and d-finite is kind of the sweet spot in the middle. We're going to force our terms to fit d-finite forms. Then we're going to extract the asymptotic information from all of them. This can be done algorithmically. I forgot to say it over there, but that d-finite asymptotics can be computed algorithmically and automatically from any d-finite function, as long as you know the linear differential equation. There is, for example, Daron has some maple code to do it, and I think Manuel Cowers has some mathematical code to do it. So that lets us do step number 2. I know I'm being vague at this point. That's intentional. The third step then is to somehow average all of the asymptotic behavior together. So this gets